Tahala Manisha, and our project stands for AI-driven register-based learning for accelerated refugee education. So it focuses on how we can use multimodal AI. Multimodal AI stands for AI. Excuse me, it stands for how we can use multimodal AI. Multimodal AI, which stands for AI combining text, images, and audio. So how we can use multimodal AI to help improve the learning of the refugee learners in Uganda under the Uganda's competence-based curriculum (CBC). And this work is done under the guidance of Mr. That one. So the contents of my presentation today, I'm going to take you to the introduction, the related work, the problem, and computational the problem statement, the research questions, contribution methodology, the description, results, photo selection, up to what we plan to do in the future. Starting off with the introduction, Uganda is home to over 1.7 million refugees, but of these, we have about 890,000 learners who are currently enrolled in schools. So these learners learn through the accelerated education program. So these accelerated education programs are programs which are designed to make learning faster, like to make learning happen faster. For example, if you're supposed to, for instance, do only for 4 years, the accelerated education program is designed for you to learn faster in about 2 years, so that you can catch up, since most these programs are designed for learners who have taken time out of school, like the refugees. So, but however, this acceleration programs first challenge is like limited resources, language barriers, and trauma-related learning gaps, and most of these are linguistically mismatched. Because if you consider refugee setting, for example, Kenya, we have learners from Sudan, those are Arabic speakers. Then we do have those from English-speaking nations, Yemen. So you find that all these learners, you have those from Congo. Then you find that all these learners have to learn using like the same material, but then they've come from different contexts, and this is some of the problems that this accelerated education programs face. So our project majorly introduces an AI-driven multimodal content authoring system that replaces manual 2D designs with visual language models and generative AI. So we do this. Excuse me. We fine-tune large vision models like the 5.5 and the mini LMs that you can generate CBC aligned, multilingual, and culture relevant lessons. By CBC, I mean the competence-based curriculum. So these acceleration programs use the competence-based curriculum. The competence-based curriculum is one which focuses on what a learner can do at the end of a particular topic in the curriculum, ignoring what they know, but they focus on what can learn. They've learned this, then what can they do? And so the output of our system is we have interactive scripts, storyboards, and lightweight 3D animations, which are designed to work offline, especially in resource-constrained environments like refugee settlements, and making them accessible for such learners. And we aim to make learning easy. So moving on to the related work. So here we refer to existing multimodal agents that have inspired our approach. So starting off with the Mini GPT-4, the Mini GPT-4 was developed to connect visual understanding with language generation. It solved the problem of describing and reasoning about images using a combination of vision encoders and large language models. This made it possible to create image-based storytelling from text prompts. And we then went on to review the Qwen 2.5. And here, this system uses an advanced multimodal by Alibaba, which are just multilingual and cross-domain understanding. So for our project, we do want to have multilingual support for the refugee settlement. So it helps guide in that area. So it enables systems to process text, image, and code efficiently using it's useful for building models that can interpret educational content in multiple languages. This is very key to our projects. And then we went into the video lemma. So in the video lemma, it extended our research further by incorporating video comprehension and temporal reasoning, solving the problem of limitation of static visuals. It can analyze and generate a sequence of frames, which helps in creating animated or dynamic content. Then we went on to the 5.5 vision and the mini LM 2.6. So Mini LM L6 V2. These are lightweight language models which are designed for low resource environments. They solve the challenge of high computation cost by offering fast, memory efficient text generation and alignment. They make them suitable for offline use, and especially since we are working in a resource constrained environment. We are developing accessible resource constrained environment. So this really guides this decision. Then we moved on to the stable diffusion. This focuses majorly on generative image creation, solving the need for visual illustration without manual design. It can create high quality, culture relevant graphics for learning materials directly from text description. Then finally, UTS, which is text to speech model, which this one helps us address the problem of accessibility and language diversity by converting text to natural multilingual voice narration, which allows learners to hear lessons in languages they can understand. Those from Arabic nations, those from English speaking nations, those from French speaking nations. This helps to guide that decision. So together, these models show how the evolution from text and image generation when multimedia storytelling so our project combines and then fine-tunes them for the CBC aligned multilingual and offline ready learning materials for refugee education. And then we moved on here. We moved on to the moving on to the problem statements. So there are majorly two core problems here in the problem statement, like the domain application problem and application problem. So for the domain problem, the refugee learners lack access to high quality, localized, and up-to-date learning materials. So the most accelerated education programs and the CBC resources are linguistically mismatched, as I had mentioned earlier, and there are also those that they're also like unavailable offline. So then the computational problem helps us in the computational problem we look at addressing how we can design an AI model that handles curriculum alignment, multilingual support, and cultural adaptation and offline optimization. So this challenge has guided our research direction, where we moved on for the research questions, the things we asked ourselves, and the objectives what we aim to achieve. So we asked ourselves 4 major questions, like how can a graphics-based framework support CBC learning for refugees? What methods can generate interactive multilingual modules that work offline? How effective are AI-generated visuals in improving engagement and retention? Then how can we create open access templates for NGOs and educators? Then our objectives are to develop a modular offline fast authoring system and to create an interactive learning module, various interactive learning modules, then to evaluate learner outcomes, because we aim to have a feedback-driven system that we keep on iterating and we keep on helping different learners depending on the feedback we get. So we need to evaluate them consistently and get feedback. And then we need to provide reusable and scalable learning templates for educators and NGOs to adapt and scale. Then our contributions, we haven't fully completed and we are still in the process of developing. So we are to develop our contributions we are to develop an offline fast modular graphics content framework for CBC aligned learning modules in low resource settings like refugee settlements. Then we are to create animated, interactive, and culturally adaptive learning models using lightweight platforms with multilingual support. And then we are to evaluate learner outcomes, including engagement, comprehension, and retention through field trials in refugee schools and centers. Then we are to create reusable visual learning objects and authoring templates for educators, NGOs, content creators to adapt, scale, and localize learning. So moving on to our methodology and architecture. As up to the video generation. So this is what our architecture is talking about today. So the process begins with a curriculum mapper, which ensures that all generated content aligns with the intended learning outcomes. So where my cursor is, right here, we have a text input, which is a teacher's input. So they simply come and say, today I'm teaching personal hygiene, say for instance. And then from that prompt, we move on to the curriculum mapper. So it ensures that the generated content aligns with the intended learning outcomes. It uses the transformer encoder to interpret the text input, the teacher's input, and compares the input with the predefined curriculum standards. So actually, the input is two-way. It can be the teacher's input or the student input, because this is meant to serve both the teachers and the students. So if they want to learn personal hygiene, they just simply an input, then the input is the curriculum mapper, which uses a transformer encoder to interpret the input text. And it does have, this is the transformer encoder, then the similarity layer. So what happens in the similarity layer is that it compares the input text with a predefined curriculum standards. So and then it outputs a curriculum aligned prompt. And so here we redefine the teacher's prompt to make sure it is aligned with the curriculum. And then a refined version of the user's input then serves as the foundation for the story generation. And then from here, we move to the story and the script generator. So here, we create a narrative flow and an instructional script. This is how the scripting occurs. So here, we combine that in the story generator. Here, we combine the token encodings and the positional. We have the token. We combine the token encodings and the positional encodings to understand the linguistic context, and then we use a multi-head self-attention to capture the relationship between the words and the phrases. So then here we have a script that, from here we produce a script that is coherent, and it has an educational story outline. So the script is diverse, coherent, and it has all the educational outline that is required to move on to the image generation and finally the video. So then this draft, then the script then passes through the GRAG, which is the graph retrieval augmented generation, which enriches the script with cultural and contextual relevance, producing. Then we have a culturally augmented scripts. Then from here, we move on to the text encoder and the unit denoiser. So here, the script is converted into latent representations for image and video generations. So first of all, here we have a text encoder, which embeds the script into a format that can be understandable by the visual generation modules. And then we have the unit denoisers. These are the unit denoisers that use the cross attention to align the textual meaning with the visual features. Then the output is a latent visual concept that guides the storyboard generation. And then from these two, we move on to the storyboard generator. This component is used to visualize the script into storyboard frames, which are a sequence of images showing how the lesson will unfold visually. So this script, we then have the storyboard generation. So if it is like personal hygiene, we shall have a child and a borehole, then a child holding soap, like the different frames that are going to be used to create a video. So then how the science behind the storyboard generator is that it uses an attention decoder to interpret the encoded text into visual scenes. And then we have a vocoder that converts the narration into a narration audio file. Then we have the VAE decoder, which is variational autoencoder that generates the advanced details and storyboard frames. So the result here, we have a narrated storyboard, which is the skeleton of the instructional video. And then from this, we move on to the lip sync encoder and the generator. This is where my cursor is. So at this stage, we synchronize the facial movements in the generated video with the narration video, such as the animation is speaking, the generated video does not come later or it doesn't come first, but they are in sync, like they are parallel, like to each other. Parallel, but they are in sync. Everything is happening at the same time. I'm sorry. And so at this stage, at the lip sync encoder, we synchronize the facial movements in the generated visuals with the narration audio. So the science behind this is that the first encoder processes the visual character's face, and then the audio encoder extracts features from the narration audio. And then the sync net discriminator, this ensures that the lip movements and the audio are perfectly aligned. And the lip sync generator then produces a synced video clip. And then finally, we move on to the video composer, where all components come together into all components. Everything comes alive in the video composer, where the video is generated. So the science behind it is that it has a timeline sequencer. Oh, sorry. This is a timeline sequencer that arranges the storyboard scenes in order, like first get the soap, then from the soap you open the borehole, from the borehole you have the soap into your hands, and after your hands you open the water, things like that. Because I know how to do mushrooming. It arranges the storyboard scenes in order. Then you have a transition engine that it adds smooth transitions and visual effects. Then after, it produces the final instructional video, which is fully synced, culturally relevant, and curriculum aligned learning assets. So in summary, giving a wrap up to our methodology and system architecture, it combines natural language processing, computer vision, audio synthesis to generate an education. Then moving on to the dataset description. Our dataset comes from Uganda's competence-based curriculum, specifically the AEP Level 1, Term 1. It has 26. We do have 26 level records from the Accelerated Education Program, Level 1, Term 1. And then we have our target variables, typically the competences which define the skill or ability a learner is expected to acquire. And then the features, it includes 13 features, which are subject, the level, the time, the topic number, the topic title, duration, overview, competency, and the learning objectives and the success criteria. Then we do have the activities and assessments, and then the hints to the teacher. And we did perform an exploratory data analysis. We did perform an exploratory data analysis, and from the results of our Accelerated Education Program Level 1 data set under the CBC, starting off with the chart, here we have the distribution by level. All entries belong to the AEP Level 1, confirming that our data set is focused and consistent for the first learning stage. And then we have the distribution of competencies with text length. And then here it shows that most competencies are short and concise, typically under 200. Here, most of them are short and concise and are typically under 200 characters, with only a few longer ones exceeding 1,000 characters. And then, so this helps us understand that the competencies are generally straightforward, making them easier for models to process and align with the learning objectives. So similarly, the distribution by term indicates that the data comes from term 1, ensuring uniformity and consistency. This is the distribution by term. And then moving on to the lower charts down here, the top 10 most frequent topics. Here I will show that the lessons like working with integers, fractions, percentages, and decimals, and rectangular Cartesian coordinates, these topics, these ones appear more often. So these topics emphasize numeracy, foundational mathematics, which are core skills targeted by early accelerated education program levels. The proportion of topics by duration, which is the pie chart here in the middle where my cursor is, it reveals that most lessons last between 4 to 8 hours, representing 80% of the data set. This consistency helps in training time and training time aware models that can generate content aligned to the real teaching schedule. Then lastly, the correlation matrix shows a weak positive correlation of 0.18 between the topic number and the competence length. It suggests that as the topic complexity slightly increases, the competence descriptions become longer, which makes sense for progressive learning content. So overall, these results confirm that our dataset is well structured, balanced, and representative of early accelerated education program mathematics content, making it suitable for fine-tuning multimodal AI models for the CBC aligned story-based lesson generation. And so here we have a few discussions. Our system generated structured lesson scripts which are aligned with Uganda's competence-based curriculum. Using semantic similarity and readability metrics, we assess the script quality with topic alignment and the relevance. The generated materials showed high semantic coherence with the topic objectives and the generated content. And then the visualization models then produced these images that I am showing, and that represented culturally familiar scenarios for the learners. This demonstrated the potential for the multimodal AI in enhancing understanding and engagement in the reflective education. So we're able to produce the images as well as the audios corresponding to the images. For the image, we use Stable Diffusion, and for the audio, we use TTS. Let me lay out one audio so that you can hear. And so that from the different storyboards, we evaluated them on the accuracy and cultural alignment and the accuracy and the cultural alignment. And then we talked about the Google TTS for the audio generation, which enabled natural voice narration with lip synced character with audio generation for the produced images. And so combining the different storyboards, we were able to come up with a video file with a video to that shows how the lesson would be conducted for mathematics. That shows how the mathematics lesson would be conducted. This is after combining all the three storyboards that are generated from the scripts together with the audios, so that both the images and the audios were combined to come up with a story-based lesson that we want to achieve. So below is a sample video. Yes, that was the sample video. So, sorry. So moving on to the model selection. Moving on to the model selection, we compared several vision language models and generative models for efficiency, quality, and offline capability, which are the Phi 3.5 and the Mini LM L6V2, which were chosen for their strong semantic understanding and lightweight nature. Then we did choose the Stable Diffusion XL, and it was selected for image generation because it produces detailed visuals and at a lower computational cost, since we want to employ our app in a low resource setting. And for the audio, we integrated the Google TTS for speech synthesis and the Web2Leap for syncing narration with the characters. So this hybrid approach balances performance with cultural adaptability and offline usability. And so for the so our project successfully demonstrated that AI-generated multimodal content can create engaging CBC-aligned lessons, and the approach enhanced storytelling and interactivity. And while the generated videos included culture-relevant images and natural voice narrations, but we are not yet doing, like, there's no motion drive yet. And so despite all the limitations, this work lays the foundation for scalable, culturally adaptive, and inclusive education. So for the next steps, we would love to transform the static images into animated scenes and sequences for the video using the video diffusion models. And then we want to conduct pilot studies with the teachers and learners to measure the comprehension and engagement and the retention capacity. And then we want to apply model quantization, pruning, and memory efficient pipelines for offline and low resource deployment as it is going to be used in the refugee settings. And then we want to include local languages like Swahili, Arabic, and any others to ensure storytelling is culturally appropriate across the refugee communities. And so we'd like to thank our supervisor, Mr. Galiwango, and our examiner for their feedback and guidance and encouragement and the continuous assessment, and ourselves for being resilient.